This problem says let y equal x plus 1 over x all to the 5th power. Part 1 says find the slope of the tangent line at the point 1, 32. And then part 2 is find all points on the graph of y where the tangent line is horizontal. So if we want to find the slope of the tangent line, we're talking about the derivative. And if we want to solve the derivative for this, we could use the binomial theorem and expand all of this, but once you've learned the chain rule, there's a simpler way to do it. We can consider part of this to be another function of some called u. So of all of this, if we call x plus 1 over x if we let u equal x plus 1 over x, then this problem is like this. And then the chain rule, which I won't show you the proof here, is if you want the derivative of y with respect to x, and you've got y as a function of u, you can do the derivative of u with respect, the derivative of y with respect to u times the derivative of u with respect to x. So we've got this and we've got this. Let's see how. First of all, if u is x plus 1 over x, then this is basically u to the 5th. Using the power rule, what is the derivative u to the 5th with respect to u? And that would be 5u to the 4th, right? And now we need to multiply this by what is the derivative of x plus 1 over x? So the derivative what's the derivative of x with respect to x? It's just 1, right? And we're adding. What's the derivative of x to the negative first? Negative 1. Or just negative x, and then decrement negative 1, so it's negative 2. Okay. So that means that if u is x plus 1 over x, then we write this. 5 times x plus 1 over x to the 4th times, now we just figured out the derivative of u with respect to x. Whoops. Is this. See, this is all of this, but we need to have this, which we figured out was this. Okay, so if this is the derivative of y with respect to x, and we want to know what is the slope at 1. And we just plug in 1 right here. 1 over 1 is 1. But look at this. If this is 1, 1 over 1 squared is 1. 1 minus 1 is 0. We don't have to do all this because anything times 0 is 0. So the slope at 1 is going to be 0. It's going to be a horizontal tangent line because the slope is 1. The slope is 0. So part 1's answer, the slope at 1, 32 is 0. Now let's remember what part 2 asks for. We want to know all the points on the graph of y with horizontal tangent. We found one of them actually with part 1. Found that at 132 the tangent is horizontal because it's the value 0. So let's look at this function and say what values of x can make this function be 0. Let's look at this part. Can this part ever be 0? What would x have to be to make this 0? Obviously 0. But if x is 0, then is 1 over 0 defined? No. So you can't make this part be 0. This part we made 0 with x equals 1. Let's write it like this. So when x equals 1, it's 0. What other value can make this be 1 so that it's, when x is 1, 1 over 1 squared is 1. 1 minus 1 is 0. What other value? Negative 1, right? Because negative 1 squared is 1. So we have negative 1. So now we have to plug negative 1 into the original function to find out what the value of y is at that function. So if this is negative 1, and if this is negative 1, we've got negative 1 minus 1. This is negative 2. What's negative 2 to the 5th? It would be negative 32 because 5 is an odd number. And there's no other value of x that will make the derivative, i.e. the slope of the tangent line, 0. So these are the points on y with horizontal tangent. This problem says find m prime of z, where m of z is 9z cubed plus 2z over the quantity 6z plus 1 cubed. So you have a choice. Do you want to do this all directly using the rules of differentiation that you know, probably the quotient rule, the power rule? You're going to have to do this. Or we can use the chain rule by figuring out any parts of this that we can consider functions of some other variable. First of all, would you rather work with a quotient rule, or would you like to work with a product rule? Personally, I think I like to work with the product rule because it's a little bit less complicated. So if I rewrite m of z like this, I'm going to write the numerator 9z cubed plus 2z times 6z plus 1 to the negative third. Now, we have something which was directly polynomial, and we have a polynomial raised to a power. We can consider let u equal 6z plus 1. Then this part would be u to the negative third, right? Then du dz would be, oh, we're not there yet. We're talking about the derivative of this would be negative 3u negative 4 times, remember the chain rule, you have to remember to do du dz. And what is du dz if u is 6z plus 1? Basically, what's the derivative of this? It's just 6. So negative 3 times 6 is negative 18u to the negative 4. But now we can replace the u right. So this is function f and this is function g. Now we've got our g prime, negative 18 6z plus 1 to the negative 4th. So that helps. Now remember the product rule. What is this going to be? If this is f and this is g, we just got to do f prime g plus f g prime. What's the derivative of 9z cubed plus 2z? We're going to use the power rule. It's 3 times 9 is 27z squared plus, what's the derivative of 2z? 2 times g. So g is just the original 6z plus 1 to the negative 3. Now we got to add, I'm going to put the symbols down here. Now what's f? It's 9z cubed plus 2z. Now we have the derivative of g prime, which we figured out using the chain rule. Okay, if this is negative 18, then I'm just going to put the negative. So it's all of this minus and I'm going to put the 18 over here and put the 6z plus 1 to the negative 4th right there. And so this is m prime of z. 27z squared plus 2 times 6z plus 1 to the negative 3rd minus 18 times 9z cubed plus 2z times 6z plus 1 to the negative 4th. And if you can factor that to make it simpler, that's spectacular. This problem says find s prime of t, where s of t equals the quantity 3t plus 4 over 6t minus 7 cubed. Now think about the chain rule as you're looking at this problem. What type of substitution would you make to make this simpler? I would say if you let some new variable u equal everything in the parentheses, 3t plus 4 over 6t minus 7, then this problem becomes, you can write it as s of u equals u cubed, u cubed, and we know with the chain rule, if we could make this be with respect to down to t would be 3u squared du dt. But let's figure out du dt first. At this point, what would you do? Is there any worthwhile substitution to make? Personally, I would just use the quotient rule and solve this directly. So I'm going to do this. Remember, the quotient rule is low times the derivative of the high. So 6t minus 7. What's the derivative of 3t plus 4? It's just 3, right? Minus the high, 3t plus 4, times the derivative of the low. What's the derivative of 6t minus 7? It's just 6, all over the denominator squared. 6t minus 7 squared. So this problem wasn't so bad. You just do 3 times this quantity, 3t plus 4 over 6t minus 7 squared, decrement 3 by 1, times, tell you what, let's write 3 6t minus 7 minus, let's put the constant in front, 6 3t plus 4 over 6t minus 7 squared. So you could simplify this if you want to. I would leave it at that. This problem says let w equal z cubed minus 2 over z, and let z be s squared plus 1 to the 5th. And the problem is to find dw ds. First of all, remember that this is a notation for a derivative function. It's not strictly a fraction of differentials, but it turns out they can be used as such. So treating the derivative notation similarly as if they were a ratio of differentials, what would you do with dw right here? Well, we know we have a function w of z. So if we took this derivative with respect to z, it would be this, right? Now, this is a function z of s. See if I can write a nice s. So if we differentiate z with respect to s, that would be dz ds. Now look at dw, dz, dz, ds. What we want to find is dw ds. Can you see what you can treat as if it's canceling out? Yes? So if we want to find the derivative of w with respect to z, what is the derivative of this? We can use the power rule here, right? This is 3z squared minus, okay, you got 2z to the negative 1. What's the derivative of this? It'd be negative 2z to the negative 2. So we've already got a minus right here. Minus, minus, we can change this to a plus. 2 over z squared. Okay, that's our dw dz. Now, we want to find out what's dz ds. What's the derivative of z with respect to s? In this case, we kind of would like to use the chain rule rather than to expand this binomial. Take a minute and pause that and see if you can figure out what substitution is best for that. So if we let some new variable called u be s squared plus 1, then z would be u to the 5th, right? Now we want to find z prime. We do 5 u to the 4th du ds. Now we just have to worry about s squared plus 1. What's the derivative of that? It would just be 2s, right? So this would be 5. Now let's put the value of u as s squared plus 1 to the 4th times the derivative of s squared plus 1, which is 2s. We can put all of this in the front. So 5 times 2s is 10s times s squared plus 1 to the 4th. And remember, what was this? This was dz ds. This is dw dz. We want dw ds. We've got dw dz and dz ds. But look, we want dw ds all in terms of s. We've got z's here, but we can just replace every instance of z with all of this. So let's do that as we write this. We're going to write dw dz, replacing all the z's with s squared plus 1 to the 5th. So we've got 3 times s squared plus 1 to the 5th squared plus 2 over, now we got z squared here, so we got s squared plus 1 to the 5th squared. This is all dw dz, right? And we have to multiply it by dz ds, which is just 10s times s squared plus 1 to the 4th. We can do some cleanup here. Simply, this quantity to the 5th and then squared would be this quantity to the 10th, right? So we can just rewrite 3 times s squared plus 1 to the 10th. Oops. Plus, what do we have here? This is all 2 over s squared plus 1, also to the 10th. So this is dw dz. And then dz ds is 10s times s squared plus 1 to the fourth. I kept these large parentheses because this is a sum. There's a lot of s squared plus 1 in here. You could possibly make this a single fraction, factor out as many s squared plus 1s as you can, but I would leave it at that. So for this problem, as you can see, we took advantage of the derivative notation as if they were ratios of differentials. Call it abusive notation, but luckily we were able to use the chain rule and come up with the solution.